Alright, hey Honors Chemistry. I wanted to provide another video on something that we're going to be learning in class briefly, and you could study from this sheet. So you're going to get a sheet that says Unit 5 Worksheet 3, and we're going to consider this extra practice. So this is not going to be done as a grade, but it can be considered scrap work. So when you go and study, there are just some extra problems for you to do, because on your next unit test, you will have to do the calculations that I'm showing you in this video. So think back to the video that I posted recently on determining the empirical formula from lab data, and now look at a question like this. It says, find the empirical formula of a compound containing 32 grams of bromine and 4.9 grams of magnesium. Okay, so I have 32.0 grams, and remember bromine is Br, and 4.9 grams of magnesium. This type of calculation has skipped all the steps that we did with the zinc and hydrochloric acid lab data. Instead of trying to figure out how much zinc and how much chlorine were in your compound, using subtraction, now they just tell you, okay, we have this compound that has 32 grams of bromine and 4.9 grams of magnesium. So, first things first, we always want to convert our grams to moles. And the way we do that is by dividing by the molar mass. Okay? Now remember, we cannot compare mass. We cannot say, oh, well, the mass of bromine is about 9 times larger than magnesium, maybe even 8 times, so I must have 8 times as much bromine. No, we cannot say that because the masses of all the elements are different. So recall, I'm going to keep on saying this, masses of all elements are different. So cannot compare by mass. Cannot compare by mass. Remember, that was Dalton. Dalton thought all elements and the atoms had the same mass. And so if I had something that was twice as massive, I must have had twice as many atoms. That's what Dalton said, and that's very outdated. So we know now that all elements have their own masses. So now let's convert 32 grams of bromine to moles. And that's by multiplying by 1 mole of bromine by its molar mass. And if you use a periodic table, you'll see that the molar mass of bromine is 79.904 grams. Okay? And I'll do the same thing for magnesium. 4.9 grams of magnesium times 1 mole of magnesium over the molar mass of magnesium is 24.305 grams. Okay? Now, if I do the math involved here, I'm going to keep on saying this. You multiply by the top number, so 32 times 1, and then divide by the bottom number, or divide by the denominator. So 32 divided by 79.904, and I get 0.400 moles of bromine. If I do my math here, 4.9 times 1, I'm going to ignore the times in 1 here. I know, but times in 1 is itself. But 4.9 times 1 divided by 24.305, I get 0.202 moles of magnesium. And in just looking at the ratio of the moles here, it appears that I have twice as many moles of bromine as I do magnesium. This ratio looks like it would be a 2 bromine to 1 magnesium ratio. And so here's how we do the empirical formula now. So I like to put kind of fake subscripts. I like to put the moles. So Mg 0.202, Br 0.400, right? I like to put these fake subscripts, and then I like to divide by the smallest moles. And remember, we put the big number on top and the small number on the bottom, and on the bottom it means I'm dividing. So I want to divide by the smallest moles. So divide by lowest moles, which is 0.202. If I do that, I'll get Mg1, and 0.4 divided by about 0.2 is Br2. This will be the empirical formula, Mg1Br2, and we know that we don't write 1 as subscript, so it should just be Mgbr2. And this would match our prediction of what the formula between magnesium and bromine would be, because we know from a past unit that the charge of magnesium is +2, and the charge of bromine is -1. That's what it forms. And so I would need 2 bromines for every 1 magnesium. So that's how we do empirical formulas. So a quick recap, and I'm going to do another one. You convert the grams that you're given to moles, and then you compare the mole ratio of one element to the other. And if you have more than one element in the compound, you're still going to divide by the smallest moles. Okay? And just by looking at this, it looks like I have 2 times as many bromine than magnesium. So how can I write a formula that has 2 bromines and 1 magnesium? MgBr2. Remember, the metal or the positive charge goes on the left, and the nonmetal goes on the right. So now let's look at something like number 2. It says, what is the empirical formula of a carbon-oxygen compound, excuse me, a carbon-oxygen compound, given that 95.2 gram sample of the compound contains 40.8 grams of carbon and the rest oxygen. So this requires a little bit of an extra step here. I know that I have 40.8 grams of carbon, okay? I know that the total mass is equal to 95.2 grams. How can I find my grams of oxygen then? Well, this compound only contains carbon and oxygen. If 40.8 grams are carbon, the difference between the total mass and the mass of carbon should be oxygen. That was just like when we got our zinc chloride. Remember that when you did the lab and you got the mass of zinc chloride and then you had the mass of zinc? So if I had the mass of zinc and I have the mass of zinc chloride, if I subtract the zinc from the zinc chloride, I'll get the mass of chloride. Well, the same thing here. If I have a carbon-oxygen compound and I have the total mass of the compound and I have the mass of carbon, if I subtract these two, now I'm going to do that on the calculator, 95.2 minus 40.8, I'll get my mass of oxygen, so 54.4 grams of oxygen. Now that I did that, right, and that's by subtraction, 95.2 minus 40.8, okay? Now that I did that, I'm going to convert my grams to moles and compare the mole ratio like we've been doing. So I'll do 40.8 grams carbon times 1 mole of carbon over 12.011 grams carbon, 54.4 grams oxygen times 1 mole oxygen over 15.999 grams oxygen. And once I get my moles of carbon and oxygen, I could compare the two of them. So 40.8 divided by 12.011, I get 3.396 moles, which is approximately 3.4 moles of carbon. And then as far as oxygen goes, 54.4 divided by 15.999, I get 3.4 moles, which is approximately 3.4 moles of carbon. Oh, sorry, oxygen, my bad. Okay, it looks like I have an equal amount of carbon and an equal amount of oxygen in this compound. So I'm going to do what I did up here, C34O34, and divide by the smallest moles. And the smallest moles is 3.4. Smallest moles, which is 3.4. So if I divide both by 3.4, I get C1O1 or CO. And that matches that I have a 1-to-1 ratio here. For every 3.4 moles of carbon, I should have 3.4 moles of oxygen. So that's 1-to-1. So I needed a formula that had equal moles of carbon and oxygen, and that is CO. Okay? I also want to show an example of doing percent composition so you could have that as a reference. There's another way of determining empirical formulas from percent composition, but I want to get us started on being able to do percent composition at the end of this video. So here's a problem. I want the percentage by mass of oxygen in magnesium nitrate. Now, you're going to see in our notes soon that the percentage by mass of oxygen is going to be the mass of O in MgNO3 divided by the mass of MgNO3 and when I say mass, I mean molar masses that are involved. I need to use the molar masses involved. So let me remind you how we get the molar masses. For MgNO3 I have 1 Mg. I have 2 N's. Don't forget that that 2 distributes on the inside, so I have 2 N's. And then I have 6 O's. So 1 magnesium's, if I have 1 magnesium or 1 mole of magnesium, if I have 1 mole of this compound, if I have 1 mole of magnesium, that mass is 24.305 grams. If I have 2 moles of nitrogen, that's 2 times 14.007 grams, which equals 14.007 times 2, I get 28.014 grams. And then I have 6 oxygens. Sorry, this is oxygen. I have 6 oxygens, which we know is 6 times 15.999 grams. 15.999. I get 95.994 grams. If I add all of these up, 1, 2, and 3, this is going to be my molar mass of the magnesium nitrate, right? Because MgNO3 has 1 magnesium, 2 nitrogens, 6 oxygens. Remember how to do molar mass. So I'm going to add these all together. 95.994 plus 28.014 plus 24.305. And I get a molar mass of 148.313 grams. Okay? Now, if I want percentage of oxygen like I said, well, I need my mass of oxygen with respect to my mass of my entire compound. So percentage of oxygen, like I said, is going to be the 95.994 grams of oxygen over the 148.313 grams of the magnesium nitrate. And we're going to do more notes on this, but I wanted to provide an example. So in doing this, I will do this part over whole, and if I want percentage, I'm eventually going to multiply by 100%. And as mentioned by some students, I believe I had a conversation with Kennedy Clark about how you calculate grades. Some of you said you don't do this times 100%, you just move the decimal point over 2 times. That's the same thing. So I'm going to do this, 95.994 divided by 148.313, and I get 0.64723, and I'm going to multiply by 100 for percentage, 64.72% oxygen. So this compound is 64.72% oxygen, right? So quickly recap how to do percent by mass. You need the molar masses of the elements and the compounds. If I want the percentage by mass of oxygen, first I needed the total mass of the whole thing, which was 148.313, and I did that by looking at the periodic table. There's 1 magnesium in here, there are 2 nitrogens in here, and there are 6 oxygens. And so I got the total mass of the entire compound, and then I got the mass of how many oxygens are in here. There were 6 oxygens, and that was 95.994 grams. So if I want to get percent by mass of oxygen in this compound, I'm going to do the 94.994 grams of the oxygen, that's where I got that from, divided by the total mass of the entire compound, and then eventually multiply by 100 percentage. Okay, so that was just a quick intro to how to do percentage by mass. Sometimes you don't even have to do the molar masses. Look at something like question 6. Question 6 says, find the percent composition of a compound that contains 17.6 grams of iron and 10.3 grams of sulfur, and the total mass is 27.9 grams. And yes, 17.6 plus 10.3 is 27.9. So if I want percentage of iron, I don't even need to do any molar mass business. It's the mass of iron over the total mass times 100%. If I want the percentage of sulfur, that's going to be the mass of sulfur over the same total mass times 100%. So let's use the numbers that they gave us in this problem. So my mass of iron was 17.6 grams of iron, divided by the total mass, which was 27.9 grams, and I could times it by 100%. So I'll do 17.6 divided by 27.9, and I get 63.08, but then times 100, I get 63.1 percentage. And then I'll do the same thing for sulfur. Sulfur is 10.3 grams sulfur over the same 27.9 grams. Again, this bottom number is the total mass. And if you remember percentages, percentage is equal to part over whole times 100%. Right? Don't forget what a percentage is, and we're going to go over percentage briefly on our next notes. And so my part is what was asked for, and my whole is the total mass of the compound. And so now I multiply by 100%, and I'll do 10.3 divided by 27.9 times 100%, and I get 36.9 percentage. And something to note, the sum of all the percentages of elements in a compound needs to add up to 100%. And 63.1 plus 36.9 adds up to 100%. So that's how you could check to make sure that you knew you did this correctly. And in looking at this, you could also use percentages to figure out the empirical formula, which is the simplest ratio. It looks like by mass, I have twice as much mass of iron than I do sulfur. But I'd have to convert that to moles. So I'd have to do something extra with this empirical formula or to find the empirical formula with the percentages. And I will show that at a later date. But for right now, if asking for percentage by mass, you just find the mass that's given or find the mass of the compound like we did in question number 8, divide by some total mass, and then multiply by 100%. Okay, so these were 2 different ways of calculating percent by mass. I'm hoping you could use this video as a reference when you're trying to do calculations or when you're trying to do practice sets, and I'm hoping you could use this video to help you study for your unit test. Alrighty, hope this was helpful.